Good morning, students. This is Addagatla Nagaraju. Lecturer in Electrical and Electronics Engineering, Government Polytechnic, Station Kanpur. Today, we are going to learn DEEE 5th semester's AC Motors subject. So in AC Motors, we are covering single phase commutator motors. Single phase commutator motors we are covering. So in single phase commutator motors, stepper motor we will cover today's lesson. Okay, so we already seen that three-phase induction motor has two types of rotors: squirrel cage type, slip ring or wound rotor type. And we also had seen that single phase induction motors are only squirrel cage type rotors, and slip ring induction motors are single phase commutator motors. In three-phase squirrel cage and slip ring, both rotors we will use, but in single phase both we will use, but cage type motors we called single phase induction motors, and slip ring type wound type rotors we call as commutator, single phase commutator motors. Single phase commutator motors. So in single phase commutator motors, previous classes we had seen AC series motor, then we had seen universal motors. Today we will see stepper motor. We will see stepper motor. So in the last class, we have learned about principle of working of single phase AC series motor, the reasons for DC series motor not working satisfactorily on AC. Okay, we also seen that principle of working of universal motor. So principle of working of AC series motor and universal motor both are same. So DC series motor cannot work satisfactorily on AC due to EMF induced in the armature. So in DC series motor only we have dynamically induced EMF in the armature, but in AC series motor, universal motor, along with dynamically induced EMF, some statically induced transformer EMF also present in the rotor. To compensate that, we use some special technique compensating windings, different techniques we had studied in the previous class. Coming to the objectives of today's lesson. So on completion of this period, you would be able to know the constructional features of variable reluctance stepper motor. Variable reluctance stepper motor. Basic controls of stepper motor. step angle, principle of operation of stepper motor. So on completion of this period, you also be able to understand the important observations regarding the principle of operation of variable reluctance stepper motor, microstepping, reduction gear stepper motor, advantages of variable reluctance stepper motor, applications of stepper motor. So, important observations regarding the principle of operation of variable reluctance stepper motor, microstepping, reduction gear stepper motor, advantages of variable reluctance stepper motor, applications of stepper motor. Coming to the introduction, a stepper motor is an electromechanical device which actuates the train of step movements of shaft in response to train of input pulses. A stepper motor is an electromechanical device which actuates a train of step movements of shaft in response to train of input pulses. The step movement may be angular or linear. Step movement may be angular or linear. There is a one-to-one relationship between an input pulse and step movement of the shaft. Stepper motor is an electromechanical device which actuates a train of step movements of shaft in response to train of input pulses. The step movement may be angular or linear. There is one-to-one relationship between an input pulses and step movement of the shaft. Each pulse input actuates one step movement of the shaft. Each pulse input actuates one step movement of the shaft. So basic controls of a stepper motor. Basic controls of a stepper motor illustrated in the figure. Drive control in that direction, forward pulse if one is forward, if zero is the input, in reverse direction, forward and reverse direction. And these are the stepping pulses. In response to the stepping input, output of the stepper motor may vary. The control has two elements: number of step pulses, which determines the angle of rotation, direction data, which determines the order in which the phases are excited. The phases are excited. Two controls: number of step pulses, direction data. Number of step pulses determine the angle of rotation. Direction data determines the order in which the phases are excited. Coming to the stepping angle, when a given number of drive pulses are supplied to the motor, when a given number of drive pulses are supplied to the motor, the shaft gets turned through a known angle. The angle through which the stepper motor turns or shaft moves for each pulse is known as the stepping angle. When a given number of drive pulses are supplied to the motor, the shaft gets turned through a known angle. The angle through which the motor turns or shaft moves for each pulse is known as the stepping angle. The step angle is expressed in degrees. Step angle is expressed in degrees. Types of stepper motors. Types of stepper motors. One is the variable reluctance stepper motor. Variable reluctance stepper motor. Second one is the permanent magnet stepper motor. Permanent magnet stepper motor. Third is the hybrid stepper motor. Hybrid stepper motor. This is the schematic arrangement of variable reluctance stepper motor. Rotor has wound type of rotor. These are the stator poles. This is the stator winding. Here it is a singleton winding. Variable reluctance stepper motor. Coming to the constructional features. It is the most basic type of stepper motor. Most basic type of stepper motor. The motor has a stator which is usually wound for 3 phases. Motor has a stator which is usually wound for 3 phases. The stator has 6 silent poles which concentrated exciting winding around each one of them. The rotor has 4 slots to produce the effects of 4-pole as shown in the figure. It is the most basic type of stepper motor. The motor has a stator which is usually wound for 3 phases. The stator has 6 salient poles which concentrated exciting winding around each one of them. The rotor has 4 slots to produce the effect of 4 poles as shown in the figure. This is the driving circuit. 3 switches, switch 1, switch 2, switch 3 are connected to 3 different poles: A dash, B dash, C dash. This is the driving circuit of stepper motor. Driving circuit of stepper motor. Variable reluctance stepper motor. The coils wound around diametrically opposite poles are connected in series. Diametrically opposite poles are connected in series. The three phases are energized from a DC source, energized from a DC source with the help of switches. With the help of switches. The basic driving circuit is shown in the figure. A stepper motor is an electromechanical device which actuates a train of step movements of shaft in response to train of input pulses. Train of input pulses. The step movement may be angular or linear. Step movement may be angular or linear. There is a one-to-one relationship between an input pulse and step movement of the shaft. Input pulse and step movement of the shaft. Each pulse input actuates one step movement of the shaft. Each pulse input actuates one step movement of the shaft. The operation is based on various reluctance positions of rotor with respect to stator. Operation is based on various reluctance positions of rotor with respect to stator. When any one of phase of the stator is excited, it produces its magnetic field whose axis lies along the pole, the phase around which is excited. Then rotor moves in such a direction so as to achieve minimum reluctance position. The operation is based on various reluctance positions of rotor with respect to stator. When any one phase of the stator is excited, it produces its magnetic field whose axis lies along the pole, the phase around which is excited. Then rotor moves in such a direction so as to achieve minimum reluctance position. Minimum reluctance position. The minimum reluctance position means position where axis of magnetic field of stator matches with axis passing through any two poles of the rotor. Minimum reluctance position means a position where axis of magnetic field of stator matches with axis of position through any two poles of the rotor. Let us see the operation when phases A and B, A, B, C are energized in sequence one after the other with the help of switches 1, 2 and 3 shown in the driving circuit. Let us see the operation when phases A, B and C are energized in sequence one after the other with the help of switches switch 1, 2, 3 shown in driving circuit. Shown in driving circuit. So here when theta is equal to 0, switch 1 is operated A and A dash, and the stator magnetic axis in the position shown here. When the phases A and A dash is excited, the switch S11 is closed, then stator magnetic axis exists along the poles formed due to A dash, that is vertical. When then rotor adjusts itself in a minimum reluctance position, that is axis of rotor poles 1 and 3 aligned with the axis of stator poles A dash shown in the figure. Rotor adjusts itself in a minimum reluctance position, that is axis of rotor poles 1 and 3 aligned with the axis of stator poles A and A dash. When the phases B, B dash is excited and phases A dash de-energized, then stator magnetic axis shifts along the poles formed due to B, B dash shown dotted in the figure B here. When the phases B, B dash is excited and the phases A dash is de-energized, then stator magnetic axis shifts along the poles formed due to B, B dash. Then rotor tries to align in the minimum reluctance position. The rotor poles 2, 4 are nearest to the position of alignment. Therefore, the rotor moves to align the axis of rotor poles 2-4 with the stator axis. This causes a rotation of 30 degrees anti-clockwise. The point P shown on the rotor has rotated through 30 degrees anti-clockwise position. 30 degrees anti-clockwise position. When the phase C dash is excited and the phases A dash and B dash are de-energized, then the stator magnetic axis shown in the figure. When the phases C dash is excited and the phases A dash and B dash are de-energized, then the stator magnetic axis shown in the figure. Then to achieve minimum reluctance position, rotor turns through further 30 degrees in anti-clockwise direction. Then to achieve minimum reluctance position, rotor turns through further 30 degrees in anti-clockwise direction. Hence, point P is now at 60 degrees from its starting position in anti-clockwise direction as shown in the figure C. By successively exciting the three phases in the specific sequence, the motor takes 12 steps to complete one revolution. 12 steps to complete. Then to achieve minimum reluctance position, rotor turns through further 30 degrees in anti-clockwise direction. Hence, point P is now at 60 degrees from its starting position in anti-clockwise direction as shown in the figure. By successively exciting the three phases in the specific sequence, the motor takes 12 steps to complete one revolution. The torque developed by the motor, which acts on the rotor is proportional to the square of the phase current. Torque is proportional to I square. The direction of rotation is decided from the sequence in which the phases are excited. Sequence in which the phases are excited. The operation of variable reluctance stepper motor is based on various reluctance positions of rotor with respect to stator. When any one phase of the stator is excited, it produces its magnetic field whose axis lies along the poles, the phase around which is excited. Then rotor moves in such a direction so as to achieve minimum reluctance position. Minimum reluctance position. The minimum reluctance position means a position where axis of magnetic field of stator is matches with the axis passing through any two poles of the motor. Two poles of the motor. So important observations. The following observations can be made from the principle of operation of stepper motor. When the phases are excited in the sequence A, B, C, A, the rotor moves in the anti-clockwise direction. When the phases are excited in the sequence A, B, C, A, the rotor moves in the anti-clockwise direction. When the phases are excited in the sequence C, B, A, C, C, B, A, C, the rotor moves in clockwise direction. The step angle alpha s is given by 360 by NP. 360 by NP. 360 by NP, where n is the number of stator poles and p is the number of rotor poles per rotor teeth. Stator poles, p is the rotor poles per rotor teeth. Rotor poles per rotor teeth. For three phases and four rotor poles, the step angle is alpha is equal to 360 by 3 into 4, that is 30 degrees. If the number of phases are increased to 4 and the number of rotor poles are 6, then the step angle 360 by 4 into 6, 15 degrees. Micro stepping. If the stator have 3 phases and 4 poles, the step angle is the 360 by 3 into 4, that is 30 degrees. We have assumed that the windings are excited one at a time if two phases are excited simultaneously. Keeping A dash excited, the B dash is also excited with switch 1 and 2 closed. Then the stator magnetic axis is access to a mid position rather than along B dash. Hence, rotor gets aligned along this, moves to a off step, that is 15 degrees. Normally, the step angle is reduced by a factor of 1 by 5th, 1 by 10th, 1 by 16th, 1 by 32. This technique is called micro stepping. This technique is called micro stepping. Further reduction in step angle can be achieved by increasing the number of poles of the stator and rotor. Further reduction in step angle can be achieved by increasing the number of poles of the stator and rotor, or by using reduction gear mechanism. Reduction gear mechanism. Reduction gear stepper motor. Both the stator and rotor have a toothed structure shown in the figure. Each stator may have 2, 3 or 4 teeth. Each stator may have 2 or 3 or 4 teeth. Rotor has more number of teeth. Example 10, 12 or 18 depending upon the step angle. Depending upon the step angle. When the stator and rotor teeth are aligned, the reluctance of the magnetic structure is minimum. If a stator is designed for 4 phases, that is 8 poles, and rotor has 18 teeth and 18 slots uniformly distributed around. If a stator is designed for 4 phases, that is 8 poles, and rotor has 18 teeth and 18 slots uniformly distributed around. When any one of the 4 phases is energized, then the electromagnetic torque produced changes rotor position such that rotor teeth under excited phases are aligned to the stator tooth of the same excited phase. When any one of the 4 phases is energized, then the electromagnetic torque produced changes rotor position such that rotor teeth under excited phases are aligned to the stator teeth of the same excited phase. With this arrangement, the step angle reduced to 5 degrees. Step angle reduced to 5 degrees. When the next phase energizes and the previous one de-energizes, the rotor is rotated through a step angle and this sequence is repeated. When the next phase energizes and the previous one de-energizes, the rotor is rotated through a step angle and this sequence is repeated by choosing different combinations of number of rotor teeth and stator phases. Any desired step angle can be achieved. Any desired step angle can be achieved. Coming to the advantages, the variable reluctance stepper motor has following the advantages: high torque to inertia ratio, high rate of acceleration, fast dynamic response, simple and low cost machine. Rotor construction is robust due to absence of brushes. High torque to inertia ratio, high rate of acceleration, fast dynamic response, simple and low cost machine. Rotor construction is robust due to absence of brushes. Coming to the applications of stepper motor, due to its capability with digital equipments, its market is greatly increased in recent times. These are widely used in XY plotters and recorders, floppy disk drives, numerical control of machine tools, process control systems, robotics, printers, tape drivers, spacecraft, and digital watches, etc. Coming to the summary, when stator phases are excited in the sequence ABCA, the rotor moves in the anti-clockwise direction. When the stator phases are excited in the sequence CBAC, then the rotor moves in clockwise direction. The step angle alpha S is equal to 360 by NP. When the stator phases are excited in the sequence ABCA, the rotor moves in the anti-clockwise direction. When the stator phases are excited in the sequence CBAC, the rotor moves in clockwise direction. The step angle alpha S is equal to 360 by NP, where N is the number of stator poles and P is the number of rotor poles per tooth. The stepper motor is designed to rotate by a specific number of degrees in response to input pulses. Step angle, it is dependent on the displacement of the rotor in response to the each input pulse. And we have discussed in this class about principle of operation of variable reluctance stepper motor. If the two stator phases are excited simultaneously, step angle is reduced. This is called micro step angle. Normally, the step angle is reduced by a factor 1 by 2, 1 by 5, 1 by 10, 1 by 16 or 1 by 13. This technique is called micro stepping. This technique is called micro stepping by choosing different combinations of number of rotor teeth and stator phases. Any desired step angle can be achieved. Any desired step angle can be achieved. Stepper motors are used in XY plotters, tape drivers, printers, floppy disk drives, etc. Coming to the quiz, the torque developed by the motor which acts on the rotor is proportional to the dash of the phase current. Option A equal, option B square, option C tries, option D none of this. So answer is the square. The output of a stepper motor is in the form of option A linear movements, option B angular movements, option C either A or B, option D none of the above. Output of a stepper motor in the form of angular movements or linear movements, either angular movements or linear movements. Output of a stepper motor. Which type of motor is most suitable for a computer printer drives? Computer printer drives. Option A shaded pole motor. Option B stepper motor. Option C universal motor. Option D split phase motor. So which type of motor is most suitable for a computer printer drive is the stepper motor. Sorry. Computer printer drive split phase motor. Computer printers applications. see the sixth, printers. So computer printers, stepper motor, speed is wrong answer. Stepper motor is the correct answer. Coming to the frequently asked questions, state the expression for the step angle. List the advantages of variable reluctance stepper motor. State the applications of stepper motor. What is a stepper motor? Explain the basic concepts of a stepper motor. What is a step angle? Explain the principle of operation of stepper motor. Okay. So if you have any doubts regarding this topic, you can mail me at nagaraju.addagatla@gmail.com. You can contact me on my WhatsApp 9866930004. Thank you.